Hi everyone, in today's video I want to show you how Cython can make your Python code dramatically faster, sometimes by a factor of 10, 50 or even 100. But instead of starting with theory, let me show you a quick demo. Here I have a simple Fibonacci function written in pure Python, nothing unusual, just a loop inside a function, something you all written at some point. Let's run it and see how long it takes. As you can see, here is the result and execution time. Now let's take a look at this version of the same function but written in Cython. The logic is identical, but here I added a couple of static types so Cython can compile it down to optimize C code. Let's run this one. As you can see, the result is the same, but execution time is much faster. So this tiny change, adding a few types and compile it with Cython, already gives us a massive speedup. And that's exactly why Cython exists. You keep writing Python, but you get C-level performance when you need it. In the next part, I'll quickly explain what Cython actually is, and then we'll jump into live coding so you can see how easy it is to use. Alright, before we start coding, let's answer one simple question. What exactly is Cython? Cython is a language that looks almost exactly like Python, but it allows you to add optional type annotations that get compiled into optimized C code. So instead of running your function inside Python's interpreter, Cython turns it to a real C function behind the scenes, which usually runs much faster. The best part is that you don't need to rewrite your program in C. You write normal Python, add a few types like int or double, and Cython does the rest. It generates C code, compiles it, and produces a regular Python module that you can import just like any other package. That's why Cython is so popular in scientific computing. It gives you the performance of C, but with the readability and flexibility of Python. And in this tutorial, you'll see that the workflow is very simple. Write a pyx file, add a little typing, compile it, and enjoy the speed. Now that we know what Cython is, let's talk about why Python is slow in the first place, because it makes it much easier to understand where the performance gains are coming from. The first reason is dynamic typing. Every time you do something simple like a plus b, Python has to check the types of both variables at runtime. Is it an int, a float, maybe a subclass? What operation should it actually perform? All of that happens dynamically for every single operation. This flexibility is great for development, but it adds a lot of overhead when you're running tight loops or numeric code. Second, Python represents everything as Python objects, even integers. So inside the loop, you're not just adding two numbers, you're allocating objects, updating reference, counters, and calling methods under the hood. It's much heavier than native CPU instructions. Third, Python is an interpreted language. Your code is executed line by line by a Python virtual machine. That means each instruction goes through several layers of processing before anything actually happens on the CPU. And finally, the GIL, the Global Interpreted Lock. This lock ensures that the only one thread runs Python bytecode at a time. For many workloads, this doesn't matter, but for CPU-heavy tasks, it definitely becomes a limitation. So when you put this all together, dynamic typing, heavy objects, the interpreter, and the GIL, you get a language that's incredibly friendly to use, but not the fastest for raw number crunching. And that's where Cython helps. It lets you bypass a lot of overhead by generating optimized C code while still keeping a Python-like syntax. Alright, now let's set up Cython and jump into the live coding part. The requirements for this tutorial are Cython and setup tools. We can install it with pip install -requirements.txt that will install everything that inside requirements.txt file. And that's it. Cython is ready to use in this environment. Before we write anything in Cython, let's start with a simple Python version of the Fibonacci function. This will be our baseline to compare performance. First, we declare a function called fib that accepts integer and return integer. Then we declare our initial variables a and b. Then we iterate in a range of n. We assign b to a and the result of a plus b to b. And we return a as a result of Fibonacci function. For testing purposes, I prepared this main Python file that we will use for time measurement of our function execution. Let's run this and check the execution time. Alright, we get the result, and this is what we'll try to beat with Cython. Now let's convert the Python function into Cython version. I'm creating a new file called cythonpip. At first glance, this will look almost identical to Python, and this is intentional. The main difference is that we can add static types. Here I'm using cpdef instead of def. This means the function can be called efficiently from both Python and C, which is usually what we want in Cython. I'm also using the int type for argument. This tells Cython exactly what kind of value n is at compile time, instead of figuring out dynamically at runtime. Next, I declare in the local variables using cdef. When I write cdef long, these variables become plain C variables, not Python objects. That means no Python objects allocation, no reference counting, and no dynamic type checks inside the loop. I also declare the loop variable explicitly. This avoids creating a Python integer on every iteration, which can be surprisingly expensive in tight loops. Now we have the loop itself. Even though this looks like normal Python, Python translates this into a simple C for loop because it knows all the types involved. At this point, there is no Python interpreter involved inside the loop at all. It's just pure C code running on the CPU. And finally, we return the result. Because this is a cpdef function, Cython automatically converts this C-long back into a Python object when we return it. So the key takeaway here is this: we didn't change the algorithm at all, we only added type information. But that small change allows Cython to completely bypass Python dynamic typing, object overhead, and interpreter loop. Now we need to compile this pyx file into Python extension module. For this, we need to create setup.py file. We need to import setup from setup tools. Then we import Cythonize from Cython build. Then we need this setup function call. This tells Cython to generate C code from cythonpip pyx file and then compile it using the system compiler. Then we use this command to build our extension. When this finishes, we get a compiled tailored library, usually a .so file on Linux or macOS that Python can import like a normal module. Now let's come back to our main py file, so we can see the difference between Python and Cython implementation of the same Fibonacci function. Here I added import from Cython and changed our Python function to Cython. Now let's try to run it. And there we go, same result, but the execution time is now much faster compared to Python result. And remember, we didn't use any advanced optimization yet. No memory views, no CRAs, no pointer, arithmetic, just static typing. This is why Cython is such a powerful tool. It lets you start small and optimize only where it matters. If you enjoyed this tutorial and want to see more Cython examples, feel free to leave a comment and subscribe. Thanks for watching, and I'll see you in the next video.